Hello everyone, my name is Mangesh Tiwari. In this lecture, we are going to discuss about disk performance parameters. What are these disk performance parameters? These are criteria used to evaluate how efficiently a disk drive stores and retrieves data. The efficiency of our disk directly reflects in the application responsiveness and overall system efficiency. In simple terms, if our disk is fast, then the application would respond it correspondingly faster and the overall system efficiency would be better. Now, what parameters do exactly lie in this disk performance parameters? Parameters such as access time and data transfer rate and the input output operations per second lie in this disk performance parameter list. Now once we understand what disk performance parameters are, now let us understand why the disk performance matters, why it is so important. First, application speed. A faster input output reduces load time by 30 to 50%, directly boosting the application speed. As we have already seen that input output operations per second lies within the disk performance parameters, a faster input output can reduce the load by 30 to 50% times. Another thing is database reads. A 2x faster disk allows 1.5x more transactions per second, improving database performance. Means the fast working of our disk help in database performance and increase the efficiency of our database. Virtual virtualization crucial. High input output enables 20% higher VM density, vital for virtualization and cloud environment. Another point is avoid bottlenecks. Slow disk can cap CPU utilization at 60 to 70%, creating system bottlenecks. Now you might be wondering, what is this term bottleneck? Bottleneck is the term which we use when the system cannot fill the requirements of the user. Now let us understand all these parameters one by one. So the first parameter is seek time. Now what is seek time? Seek time is the amount of time taken to move the read-write head from its current position to the desired track. Now let's take these as an example. Consider this as a surface of a disk. Let's say it is the upper surface of the disk and it is a read-write head. So let's say I have stored my data in this particular track. The time it would take to move this read-write head to my required track or my desired track is known as seek time. Seek time is the delay for read-write heads. We have seen here the read-write head. So the time it would take to move the read-write head to our particular desired track is known as seek time. It impacts random read and write operations on HDDs. SSDs have near zero mechanical seek time, typically less than 0.1 millisecond access. This is because SSDs don't use mechanical heads to read and write their data. Now our next parameter is rotation latency. Let us understand what is rotation latency. After some seek time, let's say our head is moved to the correct track where we have stored our data. So let's say I have stored my data in these particular sector. So the time it would take to rotate this sector directly under the
read-write head so that the header could read and write the disk. So the rotation latency's definition goes like the amount of time taken to rotate the track when the read-write header comes to exact position or to the exact sector. Now rotation latency is the time a disk plater takes for the desired sector to spin directly under the read-write head. As I've already told you, let's say my data is has been stored here somewhere. So my disk need to be rotated directly under the head's position so that the head could perform whatever operation it must. So my data, the other point is my data could be present here, here, or somewhere here. I don't know. So we don't know how much time it would take to rotate to the correct head's position. So we generally consider it as 1 by 2 of rotation time. Whatever the rotation time of the disk is, we consider the rotation latency to be half of it as an average. So what is the impact of rotation latency on the disk? These latency introduces a significant delay in input output operations. It directly affects the disk effective throw output, means how fast the input output operations are being performed in the disk. So faster RPM drives reduces this weight. Another parameter is throw output or data transfer rate. Now what is this data transfer rate? Once our head has been positioned to its correct place, which is directly above the required data, so the time it would take to transfer this data is known as throw output. The throw output generally depends on how fast the disk plater rotates and what's the size of track the header needs to cover to transfer the data. So data transfer rate generally measures the data transfer per second in MBs or GBs. Data transfer rate is very crucial in video streaming and large file transfers because the time matters when we are transferring large amount of files. So sequential input output maximizes the throw output. So if the sequential outputs and inputs are in sequence, so it would be comparatively very faster. Now here are some typical values for different type of disks. For hard disk it is 80 to 160 MB per second. For SATA SSDs it is 500 to 550 MB per second, and for NVMe SSD it is 3 to 7 GB per second. Upgrading to NVMe can improve the data loading by 5 to 10 times. So the last parameter is IOPS, also known as input output operation per second. Input output operation per second measures read and write operations per second, critical for transactional database and virtual machines. It means how fast the input output operations are being performed in the disk. Random input output significantly reduces the effective IOPS, means in a disk performing input output operations at random positions could reduce the effectiveness of IOPS, while highly IOPS drives, means the drives which offer a highly IOPS, reduces database query times by up to 40%. Here is IOPS for different disks. For hard disk it is 70 to 200. For SATA SSD it is 50,000 to 100,000, and for NVMe SSD it is 300,000 to a million. Now let us understand the utilization of our disk. How busy is our disk. At first, activity measure percentage of time the disk actively processes input output operations. Apart from the seek time and the rotation latency, it is the percentage of time the disk actively processes an input output operation requests. So that comes under activity measure. The bottleneck indicator, high utilization which is considered above 80 to 90% often signals a performance bottleneck. I have already told you what is a bottleneck. Bottleneck is a condition when the system cannot fill the requirements of a user. This condition occurs when our disk is highly utilized, more than 80 to 90%. Efficiency versus saturation. High utilization does not always mean poor performance. It could be efficiently used. Sustained 100% indicates saturation. Means if our disk is 100% filled with data, then it is the saturation condition. While if it's highly utilized, it doesn't mean it is of poor performance. It means we are using it efficiently. Monitoring tools. Monitor with tools like top or storage analytics platform. Now let us understand workload analysis, input output pattern. Random versus sequential. We are considering it as corresponding to input output operations. Now random versus sequential dictates impact on IOPS versus through output. Random storage would have a less IOPS, while sequential IOPS has a fast and greater IOPS. Read versus write mix determines drive wear and caching efficiency. Now block size. Smaller block size favors IOPS and larger block size favors through output, because in through output we just consider on data transfer rate, and in input output operations we basically count how many operations are being performed. So profiling tools identify predominant input output characteristics, tailor storage solution to match workload patterns. These optimal performance for specific applications and data needs. Now for the conclusion, understanding the metrics, we use these disk performance parameters to understand the metrics, master the IOPS, through output, latency, seek time and utilization for further choosing the right storage to select the based on workload. For example, the NVMe is used for high IOPS while the HDDs have large capacities. Effective performance optimization can be yield 20 to 50% gain in application efficiency. Application efficiency is very important. It determines how fast the application is responding to our system. This leads to a smoother operation and better